Okay, ji, Bismillahirrahmanirrahim. Today we are going to start our lecture, and today we are going to discuss a topic that is commonly referred to as fading. ठीक है जी? And we will study an important technique that is also referred to as orthogonal frequency division multiplexing. So actually OFDM is something that is used to overcome the problems that are created by fading. So that's why both of them will be discussed together. Fading, we have discussed previously different type of fading in which we have discussed the path loss of the signal. Now we will discuss something that is commonly referred to as multi-path fading, and we will try to understand what are the problems that are created by multi-path fading and what actually is multi-path fading. And then we will try to understand how can we overcome the problems of multi-path fading with the help of orthogonal frequency division multiplexing. So let's start the lecture. So what actually is fading? So if we want to understand the concept of fading, so fading actually refers to the time variation. Actually, you have studied previously or you have seen previously that whenever a signal is transmitted between the transmitter and receiver module, and the channel in between the transmitter and receiver module is a wireless channel. So obviously the signal undergoes through several changes. The first and the foremost change that we have discussed so far is the decrease in the power. That is, the strength of the signal or the power of the signal deteriorates as it moves from one point to another point. So obviously there are some variations introduced in the signal, and because of those particular variations, the information at the receiving end is not decoded properly. So collectively, what actually is fading? So fading actually refers to the time variation of the received signal. That is the variation that occurs in the signal with respect to time. Okay, the variations that are taking place in the signal with respect to time, or the time variation of the received signal power caused by the changes in the transmission medium or the path. Okay, so it is understood that all the changes or all the deteriorations that are taking place in the signal, the main culprit for those particular changes is the transmission medium or the transmission path that is present in between the transmitter and the receiver module. Now, there are different type of impairments that are present in the channel, and these impairments can affect the signal in different forms. So previously, we have seen that the strength of the signal or the power of the signal deteriorates as it moves from one point to another point. Today, we are going to see another type of fading, and we are going to understand how multi-path fading affects the quality of the signal at the receiving end. Now, another way of defining fading is fading refers to the distortion that a carrier modulated signal experience over a certain propagation medium. Okay, so obviously, if we are talking about a wireless communication system, so in wireless communication system, it is understood that a signal or a baseband signal or a message signal needs to be modulated with the carrier. Obviously, the signal cannot be transmitted as it is due to the problems caused by the wireless medium. So obviously, a signal needs to be modulated with the help of a carrier. And when that particular signal is modulated and it is transmitted across the channel, so obviously it faces through different type of impairments. And this type of impairments actually decreases the quality of your signal, which actually affects the information that is recovered at the receiving end. And most of these impairments or most of these deterioration factors are actually introduced by the propagation media or the channel or the wireless media that is present in between the transmitter and receiver module, with some of the noises that are being introduced at the receiving end as well. So in wireless system, the fading that we are going to discuss today is due to the multi-path propagation, and it is sometimes referred to as the multi-path induced fading or the multi-path fading. So what actually is a multi-path fading? So the multi-path fading, if you can observe the name multi-path, multi-path means that whenever a signal is transmitted from the transmitter module, so obviously it is transmitting in a wireless medium and it is transmitting with the help of an antenna, that actually emits electromagnetic waves in different directions. So the signal must propagate, or the signal might propagate in different path while reaching between the transmitter and receiver module. For example, this is your transmitter and this is your receiver. And if a signal is transmitted between the transmitter and receiver module, so obviously the electromagnetic spectrum that is transmitted from the antenna will move something like this. In other words, the signal that is traveling between the transmitter and receiver module will take several paths while moving from the transmitter side towards the receiver side. So actually, multipath refers to this particular concept, that the signal that is being transmitted from the transmitter towards the receiver actually take different paths, okay, or different copies of the signal are actually transmitted and are actually received at the receiving end because of the different paths that are taken by the signal owing to the electromagnetic spread of the spectrum and owing to the transmission of the signal over the wireless channel. So multipath, several delayed copies or several delayed replicas of the signal are arriving at the receiver. And the effect of this multipath include constructive interference. Obviously, you have multiple copies of the signal. So when these particular signals are received at the receiving end, there can be constructive interference depending on the phase difference of the signals, and there can be destructive interference. So when the signals are received constructively, so they can help or they can elevate the quality of your signal. However, if destructive interference takes place, so obviously the signal to noise ratio will be less and more errors will be introduced at the receiving end. So it is beneficial as well as it can create problems at the receiving end as well. So what actually causes fading or what actually causes problems at the receiving end? That is the constructive and the destructive interference of the signals. Since same copies, multiple copies of same signals are received at the receiving end, so those particular signals can add up constructively or they can add up destructively. If they are added constructively, it's a good thing. If they are added destructively, it can create problems in a signal. Okay, and ultimately what you will get a signal that is relatively poor in quality, that will have lower signal to noise values and that will have higher bit error rates. So what does it mean? Let's suppose a signal is transmitted between the transmitter and the receiving end, and that particular signal take multiple paths. Let's suppose one signal or one copy of the signal reaches directly between the transmitter and the receiving end. Another copy of the signal takes a relatively longer path and is reflected from the surface of the ground. Another copy of the signal is scattered from the object that is present between the transmitter and the receiver module. So actually multiple copies of the signal are received, of the same signal are actually received at the receiving end. Let's suppose this is the first copy of the signal that is received by the receiver, and this particular copy of the signal is, let's suppose, traveling through path 1. Similarly, if you can see the red signal, this is the second copy of the signal that is received at the receiving end, and let's suppose it has been traveling through path 2. So if you can see, let's suppose we can easily say that path 1, the signal is traveling directly between the transmitter and receiver module since it has a relatively larger amplitude. Similarly, part 2, the signal might have been reflected or diffracted through some other obstacles in between the transmitter and receiver module, since the amplitude of this particular signal is relatively less. Now, when both of these copies are received at the receiving end, so what happens? A constructive interference or a destructive interference might take place, and resultant signal will have a relatively larger amplitude if constructive interference takes place, and it can have no amplitude or very small amplitude if destructive interference takes place. So this creates problems at the receiving end, and we need to devise some suitable mechanisms in order to overcome this particular problem. But before devising some suitable mechanism, it is desirable to understand what actually is multipath fading and what are the reasons that are actually creating the multipath fading, and what are actually the problems that arises because of this particular multipath fading. So multipath fading or the multipath propagation actually occurs as the consequence of reflection, because if you remember previously, we have discussed free space propagation model. And in free space propagation model, we have considered an ideal scenario. Ideal scenario in a sense that there are no obstacles present between the transmitter and the receiver module, and the signal is traveling in a relatively straight line between the transmitter and the receiver module. It is not reflected, it is not diffracted, it is not scattered. It is traveling in a straight line. Okay, but in practical scenario, this is not the case. There are different obstacles present in between the transmitter and receiver module. There are different obstructions present in between the transmitter and receiver module, and the nature of the obstruction is obviously different. There can be mountains, there can be trees, there can be buildings, there can be poles, there can be electric cables, and so on. So each of these obstruction actually affects the signal differently, and based on the nature of the obstruction, you can get something that can be referred to as reflection. You can get something that can be referred to as scattering. You can get something that can be referred to as diffraction. So all of these factors add up, and all of these factors actually are responsible for the cause of multipath fading. So if you can look at this particular figure, we have a mobile station, and this mobile station is communicating with the base station. Now there are different type of obstructions present in between the mobile station and the base station, and each type of the obstruction is actually resulting in different type of mechanism. Let's suppose if a signal is reflected from a building, so it can be referred to as reflection. Similarly, we can face something that is commonly referred to as diffraction, and we can face something that can be commonly referred to as scattering as well. So we'll be discussing these things in detail, but just to give you an idea that the signal can take multiple paths when traveling over the wireless channel between the transmitter and receiver module. And the reason for the signal to take multiple paths is that there are obstructions present in between the transmitter and receiver module. And due to the nature of the obstruction, different mechanisms can take place. A reflection can happen, scattering can happen, or diffraction or shadowing can also occur in between the transmitter and receiver module. And because of all those mechanisms, multiple copies of a signal can occur, and these multiple copies can result in constructive interference, or they can result in destructive interference. So it can be beneficial and it can be problematic as well. Now, so as I said, multipath fading can be beneficial as well. Okay, it's not that it only creates problem. So it has some benefits as well, and those benefits actually allow us to communicate in between the transmitter and receiver module. For example, you are sitting inside your room and you can attend a call with the help of your mobile phone. So actually the signal is being reached to you due to reflection and several processes, because you are not in line of sight with the base station, and still you are able to receive the signal and you are able to make a call. So all of these particular phenomena are possible because of this multipath effect. So what are the positive effects of the multipath fading? So some of the positive effects of the multipath fading are: multipath fading enables communication when the transmitter and receiver are not in the line of sight condition. So as I just gave you an example, that you are sitting inside a room and you are still able to receive a call and you are still able to make calls. So this is only possible because of the multipath effect, because the signal can reach to you due to reflection or diffraction with the objects that are present in between you and the base station. So it actually allows radio waves effectively to go through obstacle or to bend across the edges of the obstacle that are present in between the transmitter and receiver module. Now, another advantage of the multipath fading is that, as I said, that multiple copies of the signal are received between the transmitter and the receiver module. And if these multiple copies are utilized effectively, they can increase the strength of your signal and they can increase the quality of your received signal by a very large quantity. So you must have heard of MIMO, there is multiple input and multiple output. So it is actually using the concept of spatial multiplexing, in which multiple copies of the signal are transmitted and those multiple copies are received and then processed accordingly to get a high quality signal. So multipath fading can also be beneficial in this particular factor, that with multiple antennas, you can capture energy that would otherwise be wasted or absorbed by the atmosphere, and you can compensate for the fades. That is, with the help of multiple antennas, you are able to receive multiple copies of the signal, and with the help of proper processing, signal processing, you can add those signals constructively, and you can get a signal with a relatively larger signal to noise ratio as compared to a system which will be using a single antenna. So, as I discussed earlier, that it is not the case that it is problematic in each and every scenario. It has its benefits, and utilizing those particular benefits, we can even increase the quality of our system and the quality of our communication. However, there are some negative effects for the multipath fading, and first and the most prominent effect of the multipath fading is the inter-symbol interference. So, what actually is inter-symbol interference? Inter-symbol interference is that when two adjacent symbols interfere with one another, so obviously this is commonly referred to as inter-symbol interference. For example, you are transmitting two bits, that is bit 1 and bit 0, okay? And this is represented with this particular symbol, and let's suppose this is represented, let's suppose, just for the sake of understanding, it is represented with this symbol, okay? Now, the first signal is used to communicate symbol 1. So it will take, let's suppose, some longer route between the transmitter and receiver module. Similarly, the second symbol is represented with signal 2, and it will reach directly between the transmitter and receiver module. So the time difference in between symbol 1 and symbol 2 as they are received at the receiving end is almost 0. So what will happen? The symbol 1 and symbol 2 will actually interfere with one another. And this is what is commonly referred to as the inter-symbol interference. When adjacent symbols actually interfere with one another. And how is this interference taking place? Because of the multiple paths that are taken by the symbol. Some symbols might take multiple paths and reach the receiver. Some symbols might be received directly between the transmitter and receiver module. So because of this particular problem, we get something that is commonly referred to as the inter-symbol interference. Now, another problem that can arise because of the multipath fading is that multiple copies of a signal may arrive at different phases. Obviously, when you are transmitting a signal, so this particular signal might take this particular path, it might take this particular path, it might take this particular path. Obviously, so multiple copies of the signal are received at the receiving end. And because of these multiple copies, some of the copies might be in phase with one another, and some of the copies might be out of phase. Okay, so if they are in phase, it is beneficial. However, if it is out of phase, so it can create something that is commonly referred to as destructive interference. And because of this particular destructive interference, you get relatively less signal to noise ratio. In other words, the strength or the power of your signal is reduced in comparison with the noises that are being introduced in the channel, or in comparison with the noises that are being introduced at the receiving end. Now, another problem that is encountered due to multipath fading or multipath effect is the random frequency modulation due to Doppler frequency shifts. Okay, so Doppler frequency shift is actually a phenomenon that takes place whenever an object is moving away, or whenever an object is moving towards the base station. Let's suppose if a mobile station, let's suppose if this is a mobile station or mobile equipment, and this particular mobile equipment is moving towards the base station, okay, with some particular velocity. So in this particular case, the signals or the spacing between the signals will be, they will be spaced closely to one another, okay, or the frequency of the signal in this particular case will be high or will be larger if it is moving towards the base station. However, if it is moving away from the base station, in this particular case, it would appear that the signal reaching the base station have a relatively lower frequency. So this particular phenomenon or this particular problem creates something that is commonly referred to as the Doppler frequency shifts. And what actually occurs in Doppler frequency shift, that is random frequency modulation due to Doppler frequency shift on the different paths. Different paths mean that if a signal or an object is moving towards the base station or it is moving away from the base station. Now, Doppler frequency shift is caused by relative velocity of the receiver to the transmitter, and it leads to frequency variations of the received signal. Okay, so if the object is moving towards the base station, it might have a different frequency. If an object is moving away from the base station, it might have a different frequency. Okay, because the velocity of an object is changing with respect to the direction it is taking towards or away from the base station, and this can affect or this can create variations in the frequency, which eventually results in multi-path fading. Okay, Ji. So any questions till this point?
No, sir.
Now we have seen earlier that whenever a signal that is transmitted between the transmitter and the receiver module, it will take different paths, because the electromagnetic signal that is being emitted from the antenna obviously spreads across its area as it moves away or as it moves between the transmitter and receiver module. Okay, hopefully you remember that particular figure in which we have an antenna, and that particular antenna is actually emitting electromagnetic spectrum, and that and the area of the spectrum is actually increasing as it is moving away from the antenna and it is moving towards the receiving antenna. Okay, so some of the signals might reach directly towards the receiving antenna. Some of the signals might take some other paths while on their way between the transmitter and receiving antennas. So the path that is taken by the signal between the transmitter and the receiver module depends on the type of the obstruction or depend on the type of the obstacles that are present in between the transmitter and receiver module. Different type of obstructions affects your signal differently and can result in different phenomena that are commonly referred to as reflection, that are commonly referred to as scattering, diffraction, and so on. So what actually is reflection? So whenever a plane waves are incident on a surface with the dimension that are very large relative to the dimension of the or relative to the wavelength of the incident waves. Okay, whenever a radio signal that is being transmitted between the transmitter and the receiver module is incident upon a surface in such a way that the size of the surface or the size of the obstacle or the size of the obstruction is very large in comparison to the wavelength of the incident wave. If the size of the object is very large in comparison to the wavelength of the incident wave, then we will get something that is commonly referred to as reflection. So if you can see over here, let's suppose we have an incident wave and that particular wave is incident over the surface of a building. So in this particular case, the size of the building is very large in comparison with the wavelength of the incident wave. And because of this particular phenomenon, this particular incident wave will be reflected from its surface. So rather than moving in a straight line between the transmitter and receiver module, this signal will be reflected between the transmitter and receiver, and obviously it will take more time while reaching between the transmitter and the receiver module. Now, another phenomenon that can take place between the transmitter and receiver is commonly referred to as scattering. Now, unlike reflection, when the incident waves or when the waves are incident on an object in such a way that the size of the object is approximately equal or less than the wavelength of the incident wave, then we get something that is commonly referred to as scattering. So scattering occurs when the plane waves are incident upon an object whose dimension are on the order of, meaning their dimension is approximately same to that of the wavelength, or their dimension is less than that of the wavelength of the incident wave, then we experience something that is commonly referred to as scattering. So if you can see over here, the incident wave is actually striking the side or the edge of the pole. Obviously, the dimension in this particular case will be less as compared to dimension or the wavelength of the incident wave. So multiple copies of the signal are generated from this particular edge of the object, and we get something that is commonly referred to as scattering. Now, another phenomenon that can take place is commonly referred to as the diffraction, and diffraction is actually the phenomenon that results in the bending of the signal. Bending of the signal means that a signal can bend from one point to another point when it reaches the edge of an obstacle. Okay, when a signal reaches the edge of an obstacle, so obviously it will bend. Either it will bend across the edge of the obstacle or it will not bend across the edge of the obstacle, depending on the wavelength of the signal. You must remember the ground wave propagation, in which we have studied that in ground wave propagation, the signal can travel over long distances. Why? Because in ground wave propagation, the signals have relatively low frequencies. Low frequency means the signal have relatively longer wavelengths. For longer wavelengths, they can be easily diffracted, they can easily bend across the edges of the surface, and because of this particular phenomenon, a signal can travel over relatively longer distances. On the other hand, if the frequency increases, so what happens? The wavelength will decrease. And if the wavelength decreases, so obviously this diffraction capability of the signal will reduce and it might not be able to bend that accurately across the edges. Yes, for example, let us just compare. Let's suppose if you are sitting inside a room and the second person is sitting inside another room, and let's suppose that that person is talking on a phone, so you can easily hear the person talking on the phone. Okay, because the frequency in that particular case is less than the frequency of the visible light that you will use to see that particular person. So you are not able to see that particular person, but you are still able to hear the sound of that particular person. It is because of the frequencies that are involved in the process of seeing and frequencies that are involved in the process of hearing. Similarly, if we talk about the Wi-Fi modules, so in case of the Wi-Fi modules, we have 2.4 gigahertz band and we have 5 gigahertz band. So 2.4 gigahertz band is more preferable because of this particular phenomenon, that it is able to bend more accurately across the edges. It has more diffraction favorable environment as compared to the 5 gigahertz band, because the 5 gigahertz band have relatively larger frequencies, and because of this particular phenomenon, it is not able to bend that accurately or that effectively, and hence it cannot cover that much distance. Now, another another phenomenon is that of the penetration, and penetration is actually the phenomenon that takes place whenever a signal penetrates to the objects. Okay, it can also be referred to as you can say shadowing effects, but penetration, obviously whenever a signal is penetrated through an object, so obviously the strength of the signal will decrease. Depending on the object, the strength of the signal will keep on decreasing if it keeps on penetrating to the objects. However, not all signals can penetrate to the objects, and not all objects can allow the signal to penetrate to them. So depending on the type of objects and depending on the type of signals that are transmitted between the transmitter and receiver module, penetration effect might vary or might be different in different cases. Okay, Ji. So that's all about multipath fading. If you have any questions till this particular point, so you can ask. We have 4 minutes in this session. So after that, new session will start, and we will start our discussion about the OFDM. But if you have any discussion or if you want to ask anything, so please go ahead. Okay. So no questions. So let me start a new session and then we will continue our discussion. Okay, Ji. So we have discussed that wherever a radio wave is transmitted uh, between the transmitter and receiver module, so it take multiple paths while reaching between these two or while reaching from the transmitter towards the receiver module. And because of this particular path, multiple copies of the signal can be received at the receiver, which can create problems by destructive interference, or you can say multiple copies of a signal can interfere with one another, resulting in intersymbol interference, which can affect the quality of your communication, which can decrease signal to noise ratio, and which can increase the bit error rates. Now, how can we overcome this? So one of the technique that is used to overcome intersymbol interference, and it is very well known technique, and it is very much used in communication technologies nowadays. If we refer to 4G technologies, if we refer to Wi-Fi technology, so most of the higher data rate technologies that are communicating with higher data rates uses this particular technology or this particular modulation scheme, and this is commonly referred to as the orthogonal frequency division. So what actually is orthogonal frequency division multiplexing, or what actually is OFDM? So if you remember the concept of code division multiple access or code division multiplexing, you might remember that in code division multiplexing, unlike simple TDM and WDM, the signal was first modulated using some particular modulation scheme like BPSK, ASK, or FSK, or QPSK. And after that type of modulation, it is again moved or sent through a second stage of modulation in which the spectrum of the signal is increased to provide some particular benefits to the communication that is being taking place between the transmitter and receiver. Now, in case of OFDM, the process is somewhat same in a sense that the signal is first modulated using some particular modulation scheme like QPSK or quadrature amplitude modulation. And after that particular process, another phase of modulation is applied, but this is different in comparison with that of OCDMA in a sense that it is more spectrally efficient as compared to that of OFDM. Now, before discussing orthogonal frequency division multiplexing, let's try to understand why is orthogonal frequency division multiplexing important and how is it different from the traditional frequency division multiplexing. So let's suppose you have a particular channel. Let's suppose you have a particular channel and that particular channel has some particular bandwidth that is P. So one of the technique for transmitting information over this particular channel is that of utilizing a signal that have approximately same bandwidth as that of the channel and transmit your entire information using that particular signal, using that particular carrier. The second approach is to divide your channel into multiple small channels or sub-channels. To divide your entire channel into multiple small channels or multiple sub-channels, and then use some particular carriers or sub-carriers in order to transmit your information over the channel. So you might remember this or you might have studied this in the topic of frequency division multiplexing, in which the entire channel is divided into smaller channels or sub-channels, and then sub-carriers are actually transmitted across each sub-channel in order to transmit information from one point to another point. So if we consider this analogy, so let's suppose if this is your entire bandwidth or this is your entire channel, and you are actually utilizing or you are actually transmitting a single carrier in order to transmit your information over this particular channel. So let's suppose you have a single truck and you are transmitting or you are sending all your load in this single truck only. So there can different problems can take place across the way. So if let's suppose if the tire is punctured or if the truck is flipped over, so all your information or all your load will be lost in this particular case. Similarly, it is not as efficient as to the process in which you subdivide or you divide your entire load and you transmit that particular load in smaller chunks or in smaller channels. Okay, so this is the basic concept. Why is it efficient to transmit your entire load into smaller channels rather than transmitting it in a single long channel? Let's try to understand this. Okay, Ji. Let's suppose we have a carrier, and that particular carrier is used to transmit information over the channel having a particular bandwidth B. So the carrier that is used to transmit information over the channel will have the same bandwidth. Let's suppose it has a bandwidth of B as well. Okay. Let's suppose that the carrier that is used to transmit information over the channel is FC. The frequency of the carrier that is being transmitted across the channel is FC. Okay, and the symbol duration or the duration of the symbol that is actually used to transmit information over the channel is 1 over B. That is the symbol duration in this particular case is 1 over B. Okay, so please try to remember these particular parameters. That is a carrier that has a bandwidth of B, okay, and it has a carrier frequency that is FC, and it has a symbol time of 1 over B. Now, let's suppose for a single channel, if we have a single channel and that particular channel has a bandwidth of 1 megahertz. Let's suppose if we have a single channel and that particular channel has a bandwidth of 1 megahertz. Okay, and you are actually transmitting a carrier in this particular channel, and that particular carrier has a frequency of FC. So the symbol duration of the carrier that you will need to transmit information across this particular channel will be that of 1 microsecond. That is T is equal to 1 over B. So 1 divided by 1 megahertz will actually give you a symbol duration of your carrier, and that particular symbol duration will be that of 1 microsecond. So this is actually the symbol that you are utilizing to transmit your information over this particular channel, which has a bandwidth of 1 megahertz. Okay. Now, previously we saw or we discussed the concept of inter-symbol interference, and we saw that whenever a signal is transmitted between the transmitter and receiver module, so it is understood that it will take multiple paths while reaching between the transmitter and receiver module. And because of this particular phenomenon, two adjacent symbols can interfere with one another, because one symbol might reach directly between the transmitter and receiver module, and the adjacent symbol might take some different paths while reaching between the transmitter and receiver module. So because of this particular phenomenon, these two symbols will interfere with one another at the receiving end, and this will result in a phenomenon that is commonly referred to as inter-symbol interference. Now, in order to overcome the problem of inter-symbol interference, we introduce some gaps between the adjacent symbols, or gaps between the adjacent symbols are introduced in such a way that, let's suppose, if one symbol is transmitted at 1 microsecond, if one symbol is transmitted at t is equal to 1 second, so the second symbol will be transmitted with a little bit delay. Okay, and this particular phenomenon is commonly referred to as the delay spread. Okay, this is commonly referred to as the delay spread, which actually tells you that there should be a gap in between the adjacent symbols, and this particular gap is intentionally introduced in order to overcome this particular problem. That is, the signal might take different paths while moving from the transmitter to receiver module. So if you have a symbol that has a duration of 1 microsecond and the delay spread in order to overcome the problem of inter-symbol interference is that of 2 microsecond, so you are actually wasting 66% of your spectrum trying to overcome the problem of inter-symbol interference via delay spread. So approximately 66% of your spectrum is underutilized, okay, in order to overcome the problem of inter-symbol interference by the concept of delay spread. Only 33% of the spectrum is efficiently utilized. The remaining 66% of the spectrum is not utilized. Okay, so this is the problem that takes place if you are using a single carrier to transmit your entire information over the channel. Okay, any question? Any question regarding this, what we have discussed so far?
No, sir.
Okay. Now, how can we overcome this? This can be overcome by dividing your entire channel into relatively small channels. And rather than using a single carrier, we use sub-carriers to transmit information over each individual channel. So what is the benefit of dividing your entire bandwidth into relatively small or narrow bandwidths or narrow channels and using relatively narrow carriers or sub-carriers in order to transmit your information? So let's suppose if you divide your bandwidth that is of 1 megahertz into relatively small channels, okay, and you use sub-carriers or different carriers in order to transmit information across each and every channel rather than utilizing a single carrier to transmit your entire information. So how is it going to benefit you? So for example, these are now your different channels, okay? These are now your different channels, and each particular channel is carrying a sub-carrier that has 10 kilohertz, okay? Sub-carrier of 10 kilohertz. So the symbol duration in this particular case will be 1 divided by 10 kilohertz. So if you solve it, you get something that is approximately equal to 100 microseconds. So you get a symbol duration of 100 microsecond in contrast to a symbol duration of 1 microsecond. Okay, in contrast to a symbol duration of 1 microsecond for a channel bandwidth that of 1 megahertz. Now we have reduced the bandwidth of the channel. So in this particular case, the bandwidth of the channel is reduced to 10 kilohertz. So in this particular case, now the symbol duration you are getting is that of 100 microsecond. Now, when you are getting a symbol duration of 100 microsecond, obviously the delay spread in this particular case will remain the same. because you will be introducing some particular delay in between the adjacent symbols in order to overcome the problem of inter-symbol interference. So the delay in between two adjacent symbols in this particular case is same, that is of 2 microseconds. However, now the entire spectrum or most of the spectrum is actually utilized in transmitting information. Only a smaller portion of the spectrum is underutilized in order to overcome the problem of inter-symbol interference using delay spread. So it easily tells you that by dividing your entire channel into relatively smaller bandwidths, you are actually increasing the symbol duration. And by increasing the symbol duration, you are actually increasing the efficiency of your communication. You are actually utilizing the available spectrum more effectively as compared to the case where you are using single carrier in order to transmit your entire information. So that is why it is more preferable to use frequency division multiplexing, or it is more preferable to use frequency division multiple access rather than transmitting your entire information with a single carrier over the entire channel. So what happens in frequency division multiplexing, or what happens in frequency division multiple access? In this particular case, your entire channel is divided into multiple channels or sub channels. Okay, and then each and every user is given a particular carrier that is commonly referred to as subcarrier, and that particular carrier is actually used by the user to transmit his or her information over the channel. However, in order to overcome the problem of inter-channel interference, because these particular channels might still interfere with one another because the signal might expand as it is traveling across the channel. So it might overlap with the adjacent channel. So in order to overcome the problem of inter-channel interference, guard bands are introduced in between adjacent channels. What actually are guard bands? Guard bands are actually unused frequencies that exist in between two adjacent channels, and these frequencies are not used. They are actually there to provide some extra room for the adjacent channels to grow as they travel between the transmitter and receiver morphage. Okay, Ji. Any questions till this point?
No, sir.
Okay. Sorry, I missed a question. Someone asked that does Wi-Fi uses FDMA? No, Wi-Fi uses direct sequence spread spectrum, and it uses orthogonal frequency division multiplexing. So we'll be discussing it in Wi-Fi when we talk about Wi-Fi. So it actually uses direct sequence spread spectrum, and it uses orthogonal frequency division. Okay. Now, so we have established till this particular point that frequency division multiplexing is more efficient for the transmission of information rather than transmitting your entire information with the help of a single carrier. But we have just seen over here that in the process of frequency division multiplexing, guard bands are introduced in between adjacent channels. And this guard band is actually unwanted. So this guard band is actually the wasted frequency. You are actually wasting your available frequency, or you are actually wasting your available spectrum in order to overcome the problem of inter-channel interference. So in order to avoid the insertion of guard band, another technique is adopted that is commonly referred to as orthogonal frequency division. Okay. Unlike frequency division multiplexing, orthogonal frequency division uses orthogonal subcarriers, or the carriers or the signal that are actually used to modulate your information are orthogonal in nature. So this orthogonality helps overcome the problem of inter-channel interference, and hence you can transmit your information without the insertion of guard bands in between your adjacent channels. So what actually is orthogonal frequency division? So in OFDM is the key wireless broadband communication technology. And what it does, unlike or rather than transmitting a high rate stream of data with a single subcarrier, like we have discussed over here, rather than transmitting a high rate stream of data with a single subcarrier, OFDM makes use of many closely spaced orthogonal subcarriers that are transmitted in parallel to one another. That is, rather than transmitting entire information using a single subcarrier, what happens in OFDM? OFDM uses many closely spaced subcarriers that are orthogonal to one another. So orthogonality is the key. Orthogonality in this particular case is the key, and it is because of this particular orthogonality that allows the user to closely space their subcarrier and that allow the user to transmit their information without the insertion of guard band in between the adjacent channels. So this combination of many subcarriers actually enable data rates like and even higher than the conventional single carrier scheme within the equivalent bandwidths. Now the subcarriers become orthogonal and they become non-overlapping to one another. So this is the example where we have frequency division multiplexing, and in this frequency division multiplexing, we have different sub channels and guard bands are introduced between each and every channel in order to overcome the problem of inter-channel interference. However, in case of OFDM, orthogonal subcarriers are used, and in orthogonal subcarriers, each and every subcarrier is closely spaced with one another without the introduction or without the insertion of guard band. So if you can see over here, almost 50% of the spectrum is still underutilized, and you can still utilize the remaining 50% of the spectrum to transmit more information. So that is why it is able to carry more information, it is able to transmit more information as compared to the existing frequency division multiplexing. So what actually is the concept of orthogonality, or how orthogonality enables the user to transmit more information by closely or by overlapping or by closely spacing or closely placing the subcarriers with one another. So what is orthogonality? So two signals are said to be orthogonal if their dot product is equal to 0, or two signals are said to be orthogonal if they are perpendicular to one another or if they are separated by 90 degrees. So two signals are said to be orthogonal if their dot product is equal to 0. So let's suppose you have two signals and you take them and integrate the signals over a particular period of time. And if the resultant is equal to 0, so you can say that both of these signals are orthogonal to one another. So let's suppose if you take two signals, we have a signal 1 over here and we have a signal 2 over here. And if you combine them together and integrate them over a given period of time, and if the end result is equal to 0, so we can easily say that both signals are orthogonal to one another. So this is the same concept that was applied in orthogonal code division multiplexers, in which two codes, when orthogonal to one another, when you combine them together, so the end result will be equal to 0. Okay. So this helps in the process if one signal is from adjacent channel and the second signal, if two signals from adjacent channels overlap, the resultant signal will be equal to 0. So it cannot affect the quality of your communication. So what is orthogonality actually? So if two signals are said to be orthogonal if their dot product is equal to 0. So this is just a simple example which is telling you when the signals are orthogonal. So if a cosine signal is multiplied with 1 and integrated over a given period of time, so you will get an output that is equal to 0. So it means that both of these signals are orthogonal to one another. Okay. Similarly, if a sine is multiplied with 1 and integrated over a given period of time, so you will get an output that is equal to 0. So it means that both of them are orthogonal to one another. Similarly, if a cosine signal is multiplied with another cosine signal such that n is not equal to m. These are, let's suppose, the frequencies of both the signals. So if the frequencies of both the signals are different in this particular case, then the signal will be orthogonal to one another. Or if one signal is actually, you can say, if let's suppose if it has a n is equal to, in this particular case, is equal to 1 and m is equal to 2 in this particular case, so the frequencies in this particular case will be different, and hence both of these signals will be orthogonal to one another. However, if we have a case in which n is equal to m, so in that particular case, both the signals will not be orthogonal and the output will not be equal to 0. Okay, ji. Any questions? Okay, no questions. I don't know. Anyways, so it's a simple concept. When two signals combine together and the end result is equal to 0, or when two signals that are perpendicular to one another are combined together and the end result is equal to 0, so it is said that they are orthogonal to one another. Okay, you can easily see over here we have, let me zoom it. We have two signals over here. One is a sine wave, okay, and this particular sine wave is represented by a blue pulse. Okay, this is represented by a blue pulse having a frequency. In this particular case, it has a frequency of 2. Okay, and another sine wave is represented by a red pulse. In this particular case, it has a frequency of 3. So actually, it is the harmonic, or red signal is actually the harmonic of this particular frequency. So it is understood that both of these signals will be orthogonal to one another. Okay. So whenever a signal is the harmonic of its previous signal, so it will be orthogonal. It will be orthogonal in nature. Okay, or they will be orthogonal with one another. Okay, ji. Any questions till this point? Okay, ji, no questions. So we have 9 minutes in this session. So let me start a new session, and after that we will resume our discussion. Okay, ji. So let's discuss some characteristics of the OFDM. So the first and the basic, or the important characteristic of orthogonal frequency division is that okay. So when a subcarrier, or when a particular subcarrier is having its maximum, the other subcarrier will have its minima or null. So this is very important characteristic of the orthogonal frequency division, and this is the characteristic that actually avoids inter-symbol interference. And we have been emphasizing again and again that all the subcarriers should be orthogonal to one another. And this is the orthogonality of the subcarriers which enables this particular characteristic. And this characteristic states that when one subcarrier is having its maximum, all the other subcarriers will have their minima. So if you can look at this particular graph, so this is the frequency domain representation of all the subcarriers. So let's suppose if we consider this particular subcarrier. So if you can see at this point, this subcarrier has its maximum. It has a maximum amplitude, it has a maximum value. And at this particular point, all the other subcarriers will have zero or will have their null, or the amplitude of all the subcarriers at this particular point will be equal to zero. So similarly, the end result will obviously, okay. Similarly, at this particular point, if you consider this subcarrier, so at this subcarrier, this point, it has a maximum amplitude. And at this point, the amplitude of all other subcarriers is equal to zero. So if we have different symbols represented by different subcarriers, so if you can see over here, only the right symbol or the correct symbol will be detected at a particular instant and all other symbols will be ignored. Hence, it can avoid or it can easily avoid the inter-symbol interference. Since at a particular instant, when the symbol is detected, all other symbols will be equal to zero. Okay, so this is the phenomenon which helps in the avoidance of the inter-symbol interference. So when a subcarrier is having its maximum, all the other subcarriers will have its minima or null, and hence the overlapping due to the delay spread is avoided. Okay. Now, all subcarriers are uncorrelated. There is no interaction of one subcarrier with another. Since they are orthogonal with one another, and because of the orthogonality, when two different subcarriers are combined together, the end result will be equal to zero. Similarly, increase in the number of subcarriers result in higher data rates and higher bandwidths. So let's suppose if you want a particular station to communicate at relatively higher data rates, so you simply assign that particular station larger number of subcarriers. So when more subcarriers are assigned, he will be able to transmit more information because more bandwidth will be allocated to that particular user. So increase in the number of subcarriers results in higher data rates and higher bandwidth. However, guard band intervals are introduced in between the subcarriers in time domain in order to overcome or in order to minimize or in order to mitigate the problem of inter-symbol interference. We have orthogonality in between adjacent subcarriers, and this orthogonality allows the fact that whenever one subcarrier is at its maximum value, all subcarriers will be at their zeros. Still, as an added measure, guard bands are introduced in between adjacent subcarriers in order to overcome the problem of inter-subcarrier. So it is an added measure in order to mitigate the problem of inter-symbol interference. Now, what is the basic operation principle of orthogonal frequency division multiplexing? Now, the first step in frequency domain, the multiple adjacent tones or multiple adjacent carriers are each independently modulated by complex data. So, first and foremost, modulation scheme like QPSK or quadrature aptitude modulation or any particular modulation scheme is actually applied or is actually utilized to modulate your data with multiple adjacent tones or subcarriers. So if you can see over here, you have your data and your data is then modulated with the help of QPSK or quadrature amplitude modulation using any particular modulation scheme that you deem fit for your particular application. Okay, so in first of all, in the frequency domain, So the multiple adjacent tones or subcarriers are independently modulated with the complex data. And these adjacent tones, they must be orthogonal to one another. The subcarriers that are being utilized in the modulation, they must be orthogonal to one another. Then in the second stage, an inverse fast Fourier transform is performed on the frequency domain subcarriers to produce OFDM symbols in the time domain. We have studied before that guard intervals needs to be introduced in between the adjacent symbols, and each symbols is actually represented by a particular subcarrier. Okay, so in order to introduce guard band in between the subcarriers, what happens? They are first, the process of inverse fast Fourier transform is applied. An inverse fast Fourier transform actually converts the signal from frequency domain to time domain. Now, when the signal is converted into time domain, then guard bands are introduced in between adjacent subcarriers. So an inverse fast Fourier transform is performed on the frequency domain subcarriers to produce OFDM symbols in time domain. Now, in the time domain, then guard intervals are inserted between each of the symbols. Okay. Now, each of the symbols that are represented by a particular subcarrier, then guard bands are introduced between each symbol in order to overcome the problem of inter-symbol interference. Then multiple symbols are combined together to create a final OFDM burst. Then multiple signals are combined together and then transmitted over the channel or the medium that is available in between the transmitted and received body. Now at the receiving end, the process is inversed in a sense that a fast Fourier transform is applied, okay, at the receiving end, and then your information is retrieved by applying the process of modulation, that is QPSK or coordination improved modulation, and your data is retrieved at the receiving. So multiple symbols can be combined to create the final OFDM burst signal, and at the receiver, fast Fourier transform is performed on the OFDM symbols to recover the original data bits, and then pass through quadrature amplitude modulation or QPSK, what is applied at the transmitter side, in order to retrieve your original information. Okay, Ji. So that's all for today's lecture. If you have any questions, so please go ahead.